My name is Basir Noordin. I'm a lecturer in the Faculty of Civil Engineering, University Technology Mara, Shah. Now I'm going to explain how to design simply supported beam. In this lecture, I'm using my slide presentation during post-conference on workshop on reinforced concrete design to Eurocode. So this is a flowchart how to design single reinforced section, whereby the first step is we have to carry out analysis to determine design moment, that is called maximum moment. Determine K value, whether the section is under reinforced or over reinforced. We have to calculate lever arm. We have to calculate tension still required based on maximum moment. We have to check minimum reinforcement requirement. And the last one, we have to check maximum reinforcement. Design procedure for a rectangular beam is, first we have to check section, whether the section is single reinforced or double reinforced. Calculate lever arm Z from equation 7.1. Calculate area of tension steel from equation 7.2. Select suitable bar size. Check minimum area of reinforcement and check maximum area of reinforcement. In beam design, we have to calculate shear reinforcement based on maximum shear from shear force diagram. So these are basically a procedure to calculate shear reinforcement for the beam. The first one, calculate ultimate design shear force VED along the beam span. Check maximum shear strength, and then calculate shear length required. And the last one, we have to provide shear length for the beam. So before we provide shear length for the beam, we have to check minimum shear length required by EC2 from equation 7.12. And shear resistance for the length based on equation 7.1. So this structure key plan that I refer for this design. The beam to be referred is beam gridline D12. So this is a structure key plan. Is prepared by structural engineer based on architectural plan. After we identify the beam gridline to be used in the design, then we start with the estimate preliminary size of beam. So how to estimate preliminary size of beam is based on span divided by 15. The span, simply supported span is 4,350 divided by 15 is equal to 290 mm. So that is overall depth of the beam, 290 mm. The width of the beam is 0.5 h, 0.5 multiplied by 290 mm is equal to 145 mm. Or we can use table NA5, assume the beam is a simply supported beam, assume concrete lightly stressed, rho is equal to 0.5%. Because it's a simply supported, L over D is equal to 20. So the effective depth D is equal to span 4350 divided by 20 is equal to 218 mm. So that is effective depth. To calculate the 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 depth of the beam section is equal to effective depth plus cover for reinforcement plus shielding plus diameter of main bar divided by 2. So the overall depth of the beam section is equal to 259 mm. So from this value, we can try beam size is equal to 150 mm based on B 145 mm multiplied by 600 mm. The overall depth of the beam section is 250 mm. Loading, we have to calculate the total of design load for the beam. So the total load of the design beam is from the slab, brick wall, and also from the variable loads. So design action for slab and is 8.6 kN per meter square. So this total design load 8.6 kN per meter square is from design load required for the slab panel. Calculate beam side weight because beam side weight is a dead load 1.35. This is a factor of dead load multiplied by beam section 0.15 meter multiplied by 0.6 meter multiplied by the density of the concrete is equal to 3 kilonewton per meter. And then because the beam is to support brick wall, so we have to consider brick wall acting on the beam. So 1.35 factor of dead load multiplied by the thickness of brick wall multiplied by the density of brick wall, then multiplied by the height of the brick wall. So is equal to 10.2 kilonewton per meter. So in this calculation, we take density of brick wall as 222 kilonewton per meter cube, thickness of brick wall 115 mm. This actually the thickness of brick wall we must take from architectural plan. So usually architect plan will inform the thickness of brick wall to be used in our design. Also floor height, we have to check from elevation of the building, floor to floor is 3000 mm. This floor height also we have to identify from architectural plan. Strength of concrete, we are using 30 Newton per mm square. So this strength of concrete is based on exposure condition. Steel strength is 500 Newton per mm square. From table 3.5, BS 8110, long span is 4350 mm, short span is 3150 mm. Design action from slab and is equal to 8.6 kN per meter square. So this data is from slab design. For case 2 adjacent is discontinuous, Ly over Lx is equal to 1.4, beta Vy is equal to 0.26 for long span discontinuous edge. So ultimate load from slab Bsy is equal to beta Vy multiplied by the design load multiplied by the short span is equal to 0.26 is from here. 8.6 is a design action load based on ultimate limit state. 3.15 is a short span. So the ultimate load from slab is equal to 7 kN per meter. Therefore, total ultimate design loads acting on the beam grid line D stroke 12 is equal to 7 kN per meter is a load from slab plus 3 kilonewton meter plus 10.2 kilonewton per meter is equal to 20.2 kilonewton per meter. So this is another method how to calculate the load acting to the beam due to slab using this formula. This is another alternative method rather than what I have explained just now. And then start calculate maximum moment and maximum shear force. The span is 4,350 mm. The total ultimate load is 20.2 kN per meter. From this simply supported beam, we have to calculate maximum moment because it's simply supported. Maximum moment is equal to WL squared over 8. The W is 20.2, L is a span, and divided by 8. So the total maximum moment is 48 kN per meter. Shear force is equal to W multiplied by the length divided by 2. So that is a shear force, maximum shear force at overside. Then calculate reinforcement. So we are using B is 150 mm. Overall depth of section, beam section is 600 mm. Cover 25 mm. Diameter main bar 20 mm. Diameter link bar 10 mm. Effective depth is equal to height of beam section 600 minus cover minus diameter link bar minus diameter main bar divided by 2. So the effective depth to be used in design is 559 mm. And then we have to check whether the section is single reinforced or under reinforced based on moment divided by B is width of the beam section, D is effective depth, FCK is concrete strength. Either we design as a rectangular section or T section or L section, we have to check the value of S is equal to 2 multiplied by D minus Z. If S is less than slab thickness, then the section designed as a rectangular section. So actually very few occasions that the neutral axis does fall below the flange. So according to this data, S is equal to 2 F559 minus 541.7 then is equal to 70.3. So this 70.3 is less than slab thickness 125 mm. Therefore, we design as a rectangular beam. So because its K value is less than 0.167, so no compression reinforcement is required. We design as a single reinforced beam. Calculate lever arm Z, and then we have to check Z must not more than 0.95 D. So that is a 531.1. And then this because Z 5.1.7 is more than 0.95 D, therefore the Z value or lever arm to be used in calculating area of steel required is using Z is 0.95 D. So therefore area of steel required is maximum moment at midspan divided by 0.87. FYK is a steel strength. Z is a 531.1. So the area of steel required is 208 mm squared. So from this AS required, we can provide 2H12 is equal to 226 mm square at bottom. 2H12 AS is equal to 226 mm square at the, for the top reinforcement. this both reinforcement is more than AS required. In design also, we have to check minimum and maximum reinforcement area. So area of steel for the minimum reinforcement is 0.3% BD is equal to 109 mm square. And then maximum reinforcement area is a 0.04 AC. 0.04 multiplied by the beam section is 3600. So just now the area of steel provided for the beam is 2H12 229 mm more than AS minimum 102, and the area of steel required for the bottom is 2H12 is equal to 229 mm square, still less than maximum area of steel 3600. Therefore, the beam section is sufficient. Next, we have to design a shear reinforcement based on maximum shear force. So from previous beam, the uniform distributed load is 20.2 kg per meter. Maximum moment at mid-span 48 kN meter. Maximum shear force at support is 44 kN. So using steel strength 500 Newton per mm square, using concrete strength 30 Newton per mm square, effective depth 5.9 mm, width of the beam section 150, overall depth of beam section is 600 mm. Then we have to calculate crushing strength, shear resistance, maximum shear resistance, VRD maximum, 0.124 BD 1 minus FCK divided by 250 multiplied by FCK. So from this maximum shear resistance more than VED, VED is based on actual load. So therefore theta is 22 degree, cot theta is 2.5. Calculate area of steel divided by S spacing. VED is based on maximum shear force divided by 0.78 multiplied by D effective depth. FYK is steel strength and cot theta. So from here, we provide 8 mm perimeter link at 300 mm center to center is equal to ASW per S 0.335. Minimum shear link is equal to 0.08 FCK, power of 0.5 BW divided by FYK, 0.131. From here, we provide 8 mm link at 300 mm center to center. ASW per S is equal to 0.335. We have to check also maximum spacing 0.75 D, 0.75 D is effective depth 419.25. So it seems that maximum spacing is 419.25, but we provide 300 mm center to center. Therefore, the link to be used is a 8 mm link at 300 mm centers is sufficient. Calculate shear resistance of the link specified is equal to 29 kN minimum. So maximum is 44 kN. So it's still within the range. Calculate deflection, percentage of required tension reinforcement based on AS required divided by beam section. Calculate reference reinforcement ratio from concrete strength. And then it seems that percentage of required tension reinforcement is less than reference reinforcement ratio. Therefore, use equation 7.16a. Factor for structural system K 1.0. This is from table 7.4n. This structural system K 1.0 is because the beam is a simply supported beam. Calculate modification factor for span is 1.0 because the span is less than 7 meters. Calculate modification factor for steel area provided, AS provided divided by AS required. Calculate allowable deflection. Calculate actual deflection. The actual deflection is less than allowable deflection. Therefore, the proposed beam size 150 mm multiplied by 600 mm is sufficient. This is a detailing of the beam. So this for the bottom bar is a 2H12. For the top bar is 2H12. For the shear link is H8 at 300 centimeters. So these are basically deflection formula to be used. This 7.16a. If rho is less than rho O, 7.16b if rho more than rho O. This is designed for fire resistant, standard fire resistant. It shows that if we use R 60 minutes, so for simply supported, so the minimum beam size is indicated here. So this basically table to be used to calculate area of steel reinforcement. That's all. Thank you very much.